Here's the answer for example 2. First, use the common ion effect. Now, what I'm going to suggest is to remove constantly the NH3 from the system. That will force the forward reaction to go to replace it. This also occurs because the reverse reaction will slow down because it has less reactants in order to go in the reverse direction. You could also use common ion effect by adding either N2 or H2, or do a combination of constantly adding both and removing the NH3. That would have the most effect on your system. In terms of temperature changes, because this reaction is exothermic, if we want it to go in the forward direction to make more ammonia, we would cool our system. This works because without the energy that we stole from the system, the reverse reaction will not have enough energy to go. And finally, let's see if we can apply a pressure change. On the left side of the equation, I have 1 nitrogen and 3 hydrogens. That's 4 gas particles. And on the right side of the equation, I have 2 ammonias. So 2. That means I'm going to put a plus pressure on the left side of the equation. If I want my forward reaction to speed up, I would increase the pressure of the system. If you increase the pressure, it favors the forward reaction because it produces less particles. Have a look in your textbook on page 396. This is how ammonia is industrially produced. It's done by using what's known as the Haber-Bosch process and uses many of the Le Chatelier shifts we've discussed in the note. Now, some students often ask, well, can we just add a catalyst to speed up the reaction and make what we want? A catalyst speeds up the rate of a reaction by lowering the activation energy. Now, since the activation energy is lowered the same amount for the forward and the reverse reaction, adding a catalyst does not cause a Le Chatelier equilibrium shift. It only reduces the time it takes for a system to achieve equilibrium once it's been disturbed.